This is the first day for the Math Operations summer course. This course goes very slow and starts off very minimal and then gradually gets into the things that you should know before entering ninth grade. So we're going to start today with place value, exponents, powers of 10, scientific notation, and comparing and ordering numbers. Your classwork / homework is also part of your notes, so we will do all of these together. So first thing is place value. Place value, this sometimes is called expanded notation when you're working with this. When you are working with expanded notation, it's just the power of 10 of each value. So if you look here, we have all the way from 1 million to 1 millionth. So anything like 1 million, 100,000, 10,000, 1,000, 100, 10, 1, those are all whole numbers. Then if you get into your decimals, you have 1/10th, 100th, 1,000th, 10,000th, 100,000th, millionth. So all of those decimal place values have that TH at the end of it. For reading whole numbers, you want to read whole numbers as if you are reading each place value. So you are reading the number 64,206,011. I'm looking right here. So you're going to begin with the largest period, which is the farthest from the left, and then read the number in this period followed by the word million, that is 64 million. Then you have 206,011. The only time you say the word and is if you have decimal places. So that and is representing that decimal point. So if we look at example 1 here, we have 2,342. This is read as 2,342. Again, no and there because there's no decimal place or decimal point. When you give this an expanded notation, it would be 2 times 1,000 plus 3 times 100 plus 4 times 10 plus 2 times 1. So it's literally each place value times that number. So because the 2 is in the thousandths, it would be 2 times 1,000. Because the 3 is in the hundreds, it's 3 times 100. Because the 4 is in the tens, it would be 4 times 10. And then because the 2 is in the ones place value, it's 2 times 1. For number 2, we have 4,236,764.325. So this is read as 4,236,764 and 325 thousandths. So if we were to just expand this, the 4 is in the millions, so it would be 4 times a million. The 2 is in the 100,000, so it's 2 times 100,000. 3 times 10,000 plus 6 times 1,000 plus 7 times 100 plus 6 times 10 plus 4 times 1 plus 3 times 1 over 10 because it's in the tenths plus 2 times 1 over 100th because it's 1 in the hundredths, and then plus 5 times 1 over 1,000. For number 3, we have 34.57. So this is 34 and 57 hundredths. So 3 times 10 plus 4 times 1 plus 5 times 1 over 10 plus 7 times 1 over 100. For 4, we have 673 and 15 hundredths. So 6 times 100, 7 times 10, 3 times 1, 1 times 1 over 10, and 5 times 1 over 100 would all be added in expanded notation. For number 5, we have 6,450,000,000,000, 1,000,000, and 2. However, that and shouldn't be there. It should just be a comma. Because again, we don't have a decimal point, so that and should not be read. So in expanded notation, the 6 would be multiplied by 1,000,000,000,000. Then your 4 would be multiplied by 100 billion. Your 5 would be multiplied by 10 billion. The 1 would be multiplied by 1,000,000. And then the 2 would be multiplied by 1, and you just add them all. If we look at 15a, we have 209. So it would just be 209. For B, we have 10,000, 6. For C, oh, I'm sorry, this was E. So let's go back. This was E. Or sorry, C, that was C. And now this is E. We'll do the ones on the left, then go to the ones on the right. So for E, we have 7.62. So this is 7 and 62. 7 and 62. Oops. That 2 is in the hundredths. So you would write hundredths. For G, that 1/10, hundredths, thousandths, 10,000. So that would just be 1/10,000ths. Moving back up to B, I'm just going to move over here for this one. For B, we have 3,000, 400, 94. For D, we have 305, 1,000, 9. For F, we have 42.6, so that's 42 and 6/10. 42 and 6/10. And for H, we have 3 and 0/10. For 16, we are writing each number in standard form. So we're writing these as numbers, not as word form. So for A, we have 565, so that's just going to be 565. For B, we have 3,500, so 3, 500. For C, we have 10 million, so that's going to be 10, 4,002. So that's 4,000. Oops, not 400,000. 004 and then 002. 10,000, or sorry, 10,004,002. For D, we have 70,901 and 1/10. So 70,000 would be 70,000. 901, so that would just be 901 and 1/10, so 0.1. For E, we have 2 and 99 hundredths. So 2, period, 99 hundredths. Make sure that second 9 is in the hundredths place. It is, so 2.99. And then for F, we have 4,090,000,000,000. So 4 trillion. You got to think, you have trillions, then billions, millions, thousands, hundreds. Okay, so trillion, 90 billion, so 090. We have to take care of our millions, our thousands, and our hundreds. Oops. For our next part of our notes for today, we are working with exponents, powers of tens, and scientific notation. So an exponent tells the number of times that base is used as a factor, which means that number of times that number, that's your whole number, is multiplied by itself. So if we look at these exponents, they are also called powers. Now we sometimes have a 2 there, which means that that number is being squared, so it's that number times itself 2 times total. Sometimes we have a 3 there. That power of 3 is also called cubed. That just means that that's the number times itself 3 times. So sometimes with these exponents, they will be negative. If they are negative, you are just taking the reciprocal of the term that it is attached to. So for example, if we have 10 to the power of negative 3, you would take the reciprocal of 10, which would be 1 over 10, and that would turn that negative 3 into a positive 3. So then it would just be 1 over 10 to the third power, which is 1 over 10 times 10 times 10. And that just simplifies to be 1 over 1,000. If you had something like 5 to the negative second power, that would become 5 to the second power if it was under 1. So it would be 1 over 5 to the second power, which is just 1 over 5 times 5, which is 1 over 25. Any number raised to the power of 0 is 1. So it doesn't matter if it's 10, 5, or 700. If it's raised to the power of 0, it is automatically 1. Just like any number that's raised to the power of 1 is that number. So if it's 10 to the power of 1, it's just 10. If it's 5 to the power of 1, it's just 5. If it's 9,000 to the power of 1, it's 9,000. The number 1 raised to any power also equals 1. So 1 to the power of 0 is 1, 1 to the first power is 1, 1 to the fourth power is 1, 1 to the 27th power is 1. If we look at our first set of examples that are done for us, it tells us for number 1, the number 7 is to be used as a factor 3 times. Write the product 2 ways. So that would be 7 times 7 times 7, or 7 to the third power, which is also 7 cubed. For 2, it asks us to write the expression 4 times 4 times 4 times 3 times 3 times 3 times 3 using exponents. Well, you see there that there's 3 4s, and then there's 4 3s. So that would be 4 to the third power times 3 to the fourth power. For 3, we're finding the value of each expression. So for A, we have 10 to the fourth power, which just means 10 times 10 times 10 times 10, which is 10,000. For B, that's 2 to the fifth power, so it's 2 times itself 5 times, which is 32. For C, that's 3 to the negative second power, so it becomes 1 over 3 to the positive second power, which is 1 over 3 times 3, which is just 1/9. Then we have D, which is 9 to the power of 0. That's just 1. Remember, any number to the power of 0 is 1. And then E is 1 to the fifth power. And remember, 1 to any power is 1. You have laws of exponents. These laws of exponents, when you are adding those exponents, as long as your bases are the same, you can add those exponents. So with this, it's like if it gives you examples, like 2 to the power of 2 plus 4 to the power of 2. You have to go ahead and do the 2 to the second power, which is 4, and then the 4 to the fourth power, which is 16, and then add them that way. You cannot add exponents unless you're multiplying. So if another example, 7 to the second power plus 7 to the third power. Yes, they have the same bases, but you cannot do this. You have to think about your order of operations. You have parentheses, then exponents. You have to simplify those exponents first before you can go into addition or subtraction. So you'd have to simplify the 7 squared, which is 49, and the 7 cubed, which is 343, before you add them to get your 392. When you are subtracting your like bases with unlike exponents, you can't subtract those unless they're evaluated first as well. So same thing, you cannot work with the subtraction unless your exponents are taken care of. So if we have 3 to the fifth power minus 3 to the second power, you have to do the 3 to the fifth power first, which is 243, and then you have to do the 3 to the second power, which is 9. Then you can subtract the 2 to get 234. For the multiplication, when you multiply powers of like bases, you can keep the base and add the exponents. This is only done if your bases are the same. So if we had 4 to the second power times 4 to the sixth power, you can do 4 to the eighth power because your base of the 4 is the same in both terms, and you're multiplying them. For your your division. In order to divide powers with like bases, you're going to keep the base and subtract the exponents. So if you had 7 to the 4th power divided by 7 squared, you can take the 7 and keep that, and then subtract the exponents. The 4 minus 2 is 2, so that's just 7 squared, which is 49. With your fractions, as long as you have the same base on the top and the bottom, you can subtract those exponents. So wherever your highest exponent is, your largest exponent, that's where your answer is going to be. So for this one, we have 2 to the 5th power over 2 to the 2nd power. The power of 5 is larger than the 2, so it's going to stay on the top of this fraction. If that 5 was in the denominator, then it would stay in the denominator. If we look at the examples that are done here for us, for 1, it tells us which of the following is not equal to 3 times 3 times 3 plus 3 times 3. So this is 3 squared. Oh, sorry, this is 3 cubed. And then the second one is 3 squared. I don't know why I keep writing that. 3 to the 3rd power. There we go. Plus 3 squared. So that one, that A is correct. You're looking for the one that's not correct. Now, you cannot add these, so that B is the one that's not correct. If you simplify the 3 cubed, that's 27. The 3 squared is 9, so the 27 plus 9 is also correct. And then if you add them, you get 36, so that's also correct. For 2, it asks which of the following is not equal to 2 to the 5th power minus 2 to the 4th power. So the 2 to the 5th power is 2 times 2 times 2 by itself 5 times, and the 2 to the 4th power is 2 times itself 4 times. So the 2 that's by itself is not equal to it. For 3, we're evaluating 5 squared times 5 cubed. So because this is multiplication, we can add those exponents. So we're going to keep the 5 and add the 2 plus 3, which gives us 5 to the 5th power. Now this is 5 times itself 5 times. When we multiply these out, we end up getting the 3,125. For 4, we're evaluating 5 to the 6th power divided by 5 squared. So we can actually set these on top of each other if we want to. So 5 to the 6th divided by 5 squared. Remember, division and fractions are the same thing, so it doesn't matter which way it's given to you, you're going to have the same answer. So because our bases are the same on both the top and the bottom, we're going to subtract these two. So it's going to give us 5 to the 4th power, which is 625. So powers of 10. When we're working with powers of 10, it's the same thing that we were doing originally. The only difference with these now is that we're actually multiplying them out. But we're looking at these powers of 10 to get an idea of where our decimals are. So it's, like I said, the same exact thing. It ties into what we started with from these notes. So these powers of 10 work with scientific notation. Your scientific notation is just a division problem that represents a multiplication problem that represents a large number. So if we look at example 1, it says a micrometer is a very small unit of length equal to 0.00003937 inch. Express this number in scientific notation. Well, if we're going from a really, really small number to a bigger number, that exponent that we're going to have is going to be negative. Remember, we want to represent a very small number, and very small numbers are negative exponents. So when we do this, we are going to move that decimal point however many places there it takes to get one single whole number to the left of it. So we're going to move 1, 2, 3, 4, 5. So because we moved 5 places, that's going to be our exponent. However, when we write this, the way that we tell if it's a positive or negative is if the number we start with is really little. So we are starting with a really little number, so this 5 is going to be negative. And then the number that's in front of this is 3.937. So it's literally just the number that we end with once we move that decimal point. For 2, we are writing the number in scientific notation, so we have 2 million. So we're going to take that 2 million and move the decimal point. Right now it's at the very far to the right. We are going to move it all the way to the left to where we just have that 2 in front of it. So we're moving 6 places. 1, 2, 3, 4, 5, 6. So this is going to be 2 times 10. We started with a large number, so it's going to be a positive 6. For 3, we have 7,800. So we're going to move that decimal point 1, 2, 3 places. So it's going to be 7.8 times 10. We started with a larger number to the positive 3. For 4, we have 0.065. We're going to move this decimal point 2 places to get 6.5 times 10 to the power of, we started with a decimal, so this exponent is going to be negative 2. So another way that your notes goes ahead and tells you to know if it's a positive or negative exponent. If a number that is equal to or greater than 1 has 10 with a positive exponent as one of the factors, and the number between 0 and 1 has 10 with a negative exponent as the factor. So again, it's the same thing that we were going over. If you're starting off with a decimal, it's going to be a negative exponent. If you're starting off with a whole number, it's going to be a positive exponent. For your next part, you have to write the number in standard form. So you're just taking that exponent and using it to move the decimal point. So for number 1, we have 2.52 times 10 to the 8th power. So since this is a positive 8, we started with a number that was large, greater than 1. So we're going to move the decimal point 8 places to the right. We're going to go 1, 2, 3, 4, 5, 6, 7, 8. And then add in zeros everywhere we added the decimal or moved the decimal point. So this is going to be 2, 5, 2, 0, 0, 0, 0, 0, 0. So our commas go every 3 zeros starting from the right and going left. So 252, comma, 0, 0, 0, comma, 0, 0, 0. For 2, it says the distance from Earth to the Sun is 7.3 times 10 to the 7 miles. So we're going to move that decimal point 7 places to the right. So 9, 3, 1. Sorry, after the 3 would be 1. Then the first 0 is 2, 3, 4, 5, 6, 7. Starting from the right going left, every 3 zeros, put a comma. So this is just going to be 93, comma, 0, 0, 0, comma, 0, 0, 0. For 3, it says a micron is equal to 1 times 10 to the negative third of a millimeter. So this 1 times 10 to the negative third, because it's negative, it's going to be a decimal ending up. So you right now have 1.0. You're going to move this 3 places, 2, 3, and then add in zeros with your decimal point. So this is just 0.001. For 4, same thing. We're starting with 3.27 times 10 to the negative fifth. So we're going to move to the left, go 1, 2, 3, 4, 5. Oops. Add in zeros. And then you're going to have 0.0000327. Your notes tell you to remember that when small numbers between 0 and 1 are written in scientific notation, the power of 10 is written with a negative exponent. If we look at number 19, it tells us if z is equal to 3 to the third power plus 4 squared plus 5 to the first power, what is the value of z? So z to the third power, or z cubed, is 3 to the third power, or 3 cubed, is 3 times 3 times 3, which is 27. The 4 squared is 4 times 4, which is 16. And the 5 to the first power is 5. So 27 plus 6 plus 5 is what we have to solve. So the 27 plus 16 gives us 43. And if we add 5 to that, this is equaling to 48. 20 says a satellite leaves Earth and travels 5.7 times 10 to the 10 to the power of 7 miles. Express the distance in standard form. So we are going from 5.7 times 10 to the 7th power. So we're moving the decimal point 1, 2, 3, 4, 5, 6, 7 places. So we're going to add in zeros. And this is going to give us 5, 7, 0, 0, 0, 0, 0, 0. So every 3. So 57, comma, 0, 0, 0, comma, 0, 0, 0. For 21, it says to express 185,000 in scientific notation, Joey wrote 18.5 times 10 to the 4th power. Was Joey's answer correct? No, it was not, because the number to the left of the decimal point has to be between 1 and 9. It cannot be greater than 9. It cannot be less than 1. And it has to only be whole numbers. So this would be 1.85 times 10 to the 1, 2, 3, 4, 5, 5th power. For 22, it says, what is half of 2 to the 10th power? Express your answer in exponential form and show your work. Well, 2 to the 10th power is 2 times 2 times 2, 10 times. So half of that, you'd be dividing it by 2. So if you did 2 to the 10th power divided by 2, that's 2 to the 1st power. So that's just 2 to the 9th power. For 23, it says in simplifying 7 to the 11th power divided by 7 to the 9th power, Alexis decides to use her calculator to find 7 to the 11th power and 7 to the 9th power individually before dividing. Show how Alexis could use the laws of exponents to arrive at the answer more easily. Well, 7 to the power of 11 divided by 7 to the 9th power is the same thing as 7 to the 11th minus the 9th power, which is 7 squared. And 7 squared is 49, so that would be your answer. When we compare and order numbers, we want to keep in mind what these numbers would be looking like or where they would be on a number line. You want to remember with a number line, anything to the left of 0 is negative, anything to the right of 0 is positive. However, you do have decimal values and fractional values in between whole numbers and in between negative integers. So with our first set of examples, it asks us if 4.9 is to the right of 3.5. So is 9 greater, or 4.9 greater than 3.5? That is true because on a number line, the 4.9 is greater than 3.5. For 2, it tells us that 0.6 is to the left of 1.3, so 0.6 is less than 1.3. To compare 2 or more whole numbers or decimals without using a number line, align the places and work from left to right. Find the first place where the number differs. So if we look at 1, in this example, we have 7.286 and 7.259. For the first place value, they're both the same. For the second place value, they're both the same. For the third, that 8 is before the 5 or greater than the 5. So the 7.286 is greater than 7.259. For 2, we're given 47.3 and 47.38. You can add in a 0 where there's not a like place value number to compare. So if we look at the first numbers from the left to the right, the 4s are both the same. The 7 is both the same. The 3 is both the same. So the 8 is greater than 0, so 47.3 is less than 47.38. 0.38. For this example, it tells us the average speeds in miles per hour of 3 cars in a race were 147.350, 150.686, and 144.317. Arrange the speeds from least to greatest. If we look at the first number from left to right with all of these, we can actually rewrite them to where we have 147.350, 150.686, and 144.317. All right, so all of our place values are lined up. Our first to the left is all ones. Then to the second place value, you have 2 4s. We're looking from least to greatest. So you're going to have to look at the number to the right of that. You have a 7 and you have a 4. So the 144.317 would go first. Then the 147.350 would go next. And lastly, the 150.686 would be put down. For 2, it tells us to replace each set of parentheses with less than or equal to, or less than or greater than, to make a true comparison. For A, we have 3.5 times 10 to the 4th power and 6.2 times 10 to the 3rd power. Well, think about this. 3.5 to the 4th times 10 to the 4th power is 3. Then 5 would be 1, 2, 3, 4. Then the 6.2 times 10 to the 3rd power would be 6. Then 2 is 1, 2, 3. So the number that is greater is the one that has the greater place values, so the 3.5 times 10 to the 4th power. For B, we have 1.15 times 10 to the 7th power. So that's 1, 1, 2, 3, 4, 5, 6, 7. Every 3. So 11, 500,000. Then we have 5.3 times 10 to the 7th power. So this is going to be 5. Then you have 3 as 1, 2, 3, 4, 5, 6, 7. Every 3. So that one's 53, comma. So which is greater, the 53, than the 11? For C, we have 4.6 times 10 to the negative 5th power. So this is going to be 4, 6. It goes to the left once, 2, 3, 4, 5. So 0.000046. For the 4, 6 times 10 to the negative 4th, we're going to have 0.00046. So which is greater? The one that has the lesser zeros is greater. So that's the 4.6 times 10 to the negative 4th. For D, we have 7.35 times 10 to the 2nd power and 7.35 times 10 to the negative 10th power. Automatically, because that 2 is positive and the negative 10 is negative, the one with the positive 2 would be greater. For 13, each letter on the number line shown represents a number. Replace each block by less than or greater than to write a true statement. So for A, we have A and Y. A is here, Y is here, Y is to the right, so Y is greater than A. For B, we have D and C, so C and D. D is to the right, so D is greater. For C, we have N and Y. Y is to the right of N, so that would be greater. For D, we have D and N, so D and N. The D is to the right of the N, so D is greater. And then N and C, so N and C, N is to the right of C, so N is greater. Then for E, we have C, A, and Y. So C, A, and Y. So C and A is greater since it's to the right. A and Y is greater since it's to the right. And then for F, we have Y, D, and A. So Y, D, and A. So between the Y and the D, the Y is to the right, so that one's going to be greater. Between the D and the D is to the right, so that one's going to be greater. For 14, it says that the table shows the average price of gasoline, of self-service regular gasoline, on the same day in several cities. Put the cities in order of price from greatest to least. So we have 1.11, 1.21, 1.07, 1.06, 1.52, 1.14, 1.29, and 1.41. We're going from greatest to least. So we want the highest one first. So all of our ones places have a 1 in them. Our tenths, though, we have a 1, a 2, a 0, a 5, a 1, a 2, and a 4. The 5 is greatest, so Los Angeles would be the first. Then from there, this is out. Choose the next greatest one with that tenths place value. You have the 4, so that's Seattle, so that's 2. That one's out. Next, you still have a 1, 2, 0, 0, 1, and 2. Your 2s are greater. So the 9 and the 1 are what's going to be compared with that. The 9 is greater, so New York would be third. Cross that one out. Then Chicago would be fourth. From there, you have 1s and 0s. Those 1s are greater than 0s, so compare the hundredths place value with those 1s in the tenths. You have a 1 and a 4, so Miami would be 5, and then Boston would be 6. Lastly, you have those 2 0s. So compare their hundredths. You have 7 and 6. 7 is greater than 6, so Denver would be 7, and then Houston would be 8. So it would be Los Angeles, then Seattle, then New York, Chicago, Miami, Boston, Denver, Houston. For 15, we are ordering each set of numbers from least to greatest. So what I'm going to do with this for A, I have 1.27 times 10 to the 7th power. So this is going to be 1, 1, 2, 3, 4, 5, 6, 7. Every 3. So 12,700,000. Then we have 5.79 times 10 to the 6th power. So 5, 7 is 1, 9 is 2, 3, 4, 5, 6. Every 3. So it's 5,790,000. Next, we have 9.3 times 10 to the 6th power. So it's 9. 3 is 1, 2, 3, 4, 5, 6. Oops, that's a 1. Every 3. So that gives us 9,300,000. So if we're putting these from least to greatest, we are going to first have the 5.79 times 10 to the 6th power. Then we have the 9.3 times 10 to the 6th power. And lastly, 1.27 times 10 to the 7th power. I'm going to do the same thing for B. So for B, we have 3.6 times 10 to the negative 4th. So I'm going to move that decimal point 4 places to the left. I'm going to have 0.00036. Then we have 4.8 times 10 to the negative 4th, so that's 0.00048. And lastly, we have 9.98 times 10 to the negative 5th, so that's 0.0000998. So we're going least to greatest. Remember, with decimals, the higher number of place values is the lesser number. So with B, with the 0.00036 and the 0.00048, they both have 5 decimal places. However, the 0.0000998 has more, so we're going to put that one first. So we're going to have 9.98 times 10 to the negative fifth first. Then we have 0.000 for both numbers, 3.6 and 4.8. The lesser of the two is the 3.6, so that 3.6 times 10 to the negative fourth would go in the middle, and the last number would be the 4.8 times 10 to the negative fourth. Oops. We want to highlight this, not erase it. So for your practice or your classwork homework for the first day, we have for number 1, the number 1, 436.06 is read as 1,436 and 6 hundredths. So C would be your answer for this one. For 2, we have 1,436.06 written as expanded notation. So the 1 is in the thousandths, so G would automatically be your answer. So it would be 1 times 1,000 plus 4 times 100 plus 3 times 10 plus 6 times 1 plus 0 times 1 over 10 plus 6 times 1 over 100. For 3, we are expanding 193.004. So this 1 is in the hundreds. We're going to do 1 times 100. So we can cross out A, we can cross out C. Then we have 9 in the tens, so that's 9 times 10. 3 in the ones, so it's 3 times 1. And then 4 is in the thousandths, so it'd be 4 times 1 over 1,000. So D is your answer. For 4, we are writing 243.708 in expanded notation. So the 2 is in the hundredths, so that's 2 times 100. The 4 is in the tens, so we're going to add 4 times 10. The 3 is in the ones, so that's 3 times 1. The 7 is in the tenths, so that's 7 times 1 over 10. And then the 8 is in the thousandths, so this is going to be 8 times 1 over 1,000. For 5, tells us the number 1.0001 is read as 1 and 1. This here, you have tenths, hundredths, thousandths, 10,000ths. So 1 and 1 10,000ths. That's A. For 6, we're asked which digit is in the tenths place. The 1 is in the tenths place. For 7, it says, given the number 6,954,209.01, identify the digit in the 10,000s place. We have ones, tens, hundreds, thousands, 10,000s. So that's the 5. For 8, we're identifying the digit in the tens place in 7,426. So the 2 is in the tens place. For 9, it says what number does 6 times 100,000 plus 9 times 1,000 plus 5 times 100 plus 2 times 1 plus 3 times 1 over 100 represent? Well, the 3 times 1 over 100 is the 3 and the hundredths place value. So B and A would automatically be crossed out. For the 6 times 100,000, that's 600,000. 9 times 1,000 is 9,000. So C would be your answer. For D, we are asked what is the value of the digit 8 in the number 3,098 430.651. The 8 is in the thousandths, so that's 8,000. For 11, we have in the world today, there are about 6,083,000,000 people. This number would be read as what? Neither of these are correct. You actually have to write it out yourself. So you have hundred, thousands, millions, billions. So it would be 6,083,000,000. For 12, we have 5,545,000,000, written in expanded notation is. So you have 100,000, million, billion. So it's 5 billion, 5 times a billion, plus 5 times 100 million, plus 4 times 10 million, plus 5 times a million. So it's going to be F here. Yes, F. For 13, it says, how much will the number 745.96 be increased if the digit 6 is changed to an 8? So this 6 is in the thousandths place. So it would be going up 2 thousandths. So A. For 14, we have which number is 11,000 more than 2.6715. 11 thousandths would be 1 here. So it would be 2.6825. So H. For 1, we have 6 to the power of 6. So this is 6 times 6 times 6 times 6. 1, 2, 3, 4 times 6 times 6. Oops. So I don't expect you to do this, but if you did 6 to the 6th power, you would get 46,656. For 2, it asks us which of the following is not correct. Well, 4 to the negative second is 1 over 4 squared. 4 squared times 4 to the 4th power times 4 to the 4th power is 4 to the 16th power. That's correct. 4 to the 4th power times 4 to the 4th power is 4 to the 8th power. And then 4 to the 10th power divided by 4 to the 5th power is 4 to the 5th power. So which of these, this one here, no, this one is not correct. So we have, this should be 4 to the 8th power. So G is not correct. 10 to the 4th power, you could do 10 times 10 times 10 times 10, or you can just say I have 4 as my exponent, so I'm going to have 4 zeros. 100 as a power of 10, you have 2 zeros, so that's 10 to the 2nd power. 1,000 as a power of 10 is 10 to the 3rd power, because you have 3 zeros. Right, 40,000 using a power of 10, so that's 4 times 10 to the 1, 2, 3, 4 power. For 7, it says there are approximately 95 million acres of farmland in the United States. Which of these is 95 million written in scientific notation? We don't have any answer choices here, so we're going to write out 95 million or 950 million. 1,000, 100. So 100,000 million. So this would be our number. If we would write this into scientific notation, it would be 9.5 times 10 to a power. So how do you know what power that is? So we move our decimal point 3, 4, 5, 6, 7, 8. So it would be 8th power. For 8, we have 2,000 written as scientific notation, so this is just 2 times 10 to the 3rd power. 1, 2, 3. 0.300 written in scientific notation is just 3 times 10 to the negative first. 0.89 written in scientific notation, 1, 2, so it's 8.9 times 10 to the negative second. Then we have 0.8296 written in scientific notation is 8.296 times 10 to the negative first. 1 million written in scientific notation is 1 times 10 to the 6th power. You have 6 zeros. For 13, you have 130. Find the value of n that makes the statement true. Okay, so 13, you have 130 times 1.3 times 10 to the power of n. So 1.3, we move that 2 places so that n is 2. 8.3, I think this is supposed to be a comma, 8,300 is equal to 8.3 times 10 to the 1, 2, 3, third place value. For 15, you have 2,589,000 is 2.589 times 10 to what power? You have 1, 2, 3, 4, 5, 6. For 16, you have 860 is equal to 8.6 times 10 to the 2nd power. And then 425,000 is 4.25 times 10 to the 1, 2, 3, 4, 5th power. For 18, we have 5 to the power of n plus 3 to the power of n is equal to 2. Well, 5 to the 2nd power is 25 plus 3 to the 3rd power is 27. That's negative 2. Or sorry, that's not negative 2. That's something greater, much greater. So let's see here. So 5, let's say 5 to the 1st power is 5 plus 3 to the 1st power is 3 equals 2. So this would have to be 1, this would have to be 1. So n is 1 for this one. For this part, we're comparing. So which comparison for number 1 is not true? So for A, we have 230 is less than 302. That's correct. For B, 7,087 is greater than 4,787. That's correct. C is 6,103 is less than. That's not true. So C is your one that's not true. For 2, it asks which group of numbers is in order from least to greatest. So for F, we have 5,648, 5,864, 5,004. That's not right. Least to greatest. For this one, the 4 is less than any other number, so that would have to be the one that comes first. For 3, we have which number is the greatest. So all of these have 5 in the thousands place except the 4, so that one will be crossed out. Moving to the hundreds, that 7 is greater than the rest, so A would be your answer. For 4, it asks what number is most likely represented by point X. So we have 11 and 15 here. So this is 12, 13, 14. So it's in between 13 and 14, so it would be 13.5. It says for 5, on a number line, which number would be to the left of 7.46? Left means less than, so it would have to be less than 7.46, so that's 7.39. 6 says a decimal with the same value as 0.59 is 0.590, so it's J. For 7 says the decimal with the greatest value is. So with this, the greatest would have to be, looking at the 3's in the 10th place, so these would be crossed out. So the hundredths, that 3 is greater than 0, so C. For 8, it says which of the decimals is not between 0.121 and 0.123. The 0.122 is, the 0.125 is, the 0.12, however, is not. For 9, it says which of the numbers is farthest to the right on the number line. So the farthest to the right is the greatest. So we have 2001, 2102, then 2012, So these would actually be out, and then this D would be the greatest. For 10, it asks which statement says that 17 is between 15 and 24. The 17 would have to be in the middle, so this one is out, so is this one. 15 is less than 17, and 17 is less than 24, so G is your answer. For 11, it says which group of numbers is in order from least to greatest. So the lesser of all of these numbers is B, the 0.068. For 12, it says how many whole numbers are between 3,099 and 4,011, not including the 2. So if we subtract these two, we would get that answer. Or you could say 3,099, then there's 4,000, that's 1. 4,001 is 2. 4,002 is 3. 4,003 is 4. 4,005 is 5. 4,006 is... Okay, let's start over again. We have 3,999. Then there's 4,000. 4,001, 4,002, 4,003, 4, 5, 6, 7, 8, 9, 10, and 11. So not including these, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that is all of your first day notes and practice for this math operations course. That is